Can you cross all 7 bridges each exactly once and walk a full loop around the city? Let's travel back to 18th century Prussia. This is the story of a city built on a river. The city was called Königsberg, and the Pregel River ran straight through its heart. In the middle of the river sat 2 large islands, with broad stretches of land on either side. 7 bridges linked those 4 landmasses, 2 to the north, 2 to the south, and 3 more. Every weekend, the townspeople made a little bet on their stroll, just for fun. There are exactly 3 rules. Break even one of them and the walk fails on the spot. Weekend after weekend, crowds went down to the river and tried to walk the route themselves. But not a single person ever succeeded, and so it became the city's long-standing puzzle. And no one had proven it impossible either. Maybe the route was simply never found. No amount of walking could reach the answer. So the greatest mathematician of the age stepped in to end the riddle. Now Leonhard Euler takes the stage. But he never once went down to the river. Euler's real genius wasn't walking harder than everyone else. It was the exact opposite. How big the land is, how wide the river is, how long each bridge is, none of it matters. Only one thing decides the route: which landmass is connected to which and by which bridge. So Euler turned the 4 landmasses, 2 islands and the 2 banks, into 4 dots. The 7 bridges become 7 lines joining those dots. That is all that's left of the map. Areas and lengths are gone, yet the problem is untouched. All that remains is connection. Let's name them. A is the north bank, B the east island, C the south bank, and D the central island. On the left, the real city. On the right, what Euler saw. Same information but nothing extra on the right. The moment distance and size were stripped away and only connection remained, graph theory was born. This simple picture is the backbone of modern route finding, network analysis, and countless algorithms. This picture of dots joined by lines? It's actually a game we all played as kids. It's the one-stroke drawing puzzle. Exactly the same problem as crossing each bridge exactly once. 3 rules. Never lift the pen, never trace the same line twice, and cover every line. So let's try it ourselves. Start at A and cross the bridges one at a time. The first 6 go smoothly, but that 6th crossing leaves you standing on the central island, D. All 5 bridges at D are already used up. There's no way out. And one bridge, the one linking C and B, is left stranded, never crossed. Change the order and try again, and one is always left behind. It wasn't bad luck. Dig into why, and a startlingly simple rule comes into view. To pass through a piece of land, you need 1 bridge coming in and 1 bridge going out. Which means bridges are always used up in pairs. 1 in, 1 out. So any spot that is neither the start nor the end must have an even number of bridges. Let's nail down one term here. The number of edges at a vertex is called its degree. It sounds technical, but it's just the bridge count. Now let's split even from odd. So what about land with an odd degree? Exactly 1 bridge is left over with no partner. So a vertex holding that unpaired bridge can only be the start or the end of the journey. But a single route has at most 2 endpoints, a start and a finish. Never 3. And that gives a rock-solid conclusion. At most 2 odd vertices are allowed. Put it all together, and the absolute law of one-stroke drawing is complete. With 0 odd vertices you get an Eulerian circuit. Cross every bridge and land right back where you started. Exactly 2 gives an Eulerian path. Start at one odd vertex, finish at the other. 4 or more is impossible. Now let's hold this law up against Königsberg. We start by counting all 4 landmasses. Counting the degree is easy. Just count the bridges touching that piece of land. The north bank A has 2 bridges to the central island and 1 to the east island. That's 3. C and B are 3 as well. Then the central island E. 2 to the north, 2 to the south, 1 to the east. That adds up to 5. Now line up the 4 numbers. 3, 3, 3 and 5. Every one of them is odd. Look at the bar chart. Every single bar is red, meaning all 4 landmasses are odd. If counting by hand feels shaky, let the code count too. A few lines of Python and it's done. The degrees add up to 14, exactly twice the number of bridges. And the odd vertices, 4 just as expected. The law allows at most 2 odd vertices. Here there are 4, twice the limit. And here Euler declares it flatly. It isn't that nobody found the route. There is no answer. It isn't that a cleverer route was missing. The townspeople roamed the riverbank hunting an answer that never existed. Now let's pick up one small fact. It looks trivial, but everything hinges on it. Add up the degrees of every vertex. The total comes out to exactly twice the number of bridges. The reason is almost too simple. Every bridge gets counted once at each of its 2 ends. Let's check that against Königsberg. The 4 landmasses had degrees 3, 3, 3, and 5. Add them all up and you get 14. There are 7 bridges and twice 7 is 14 as well. It lines up exactly. This simple little identity even has an elegant name. It's called the Handshaking Lemma. A handshake always takes 2 people. So if you count every hand that was offered, the total is always even. And from this, one conclusion falls right out. A rather surprising one. The total of all degrees is even. The even degrees sum to an even number, so the odd degrees left over must sum to an even number too. But add up an odd number of odd numbers and the total is odd. So odd vertices can only come in even counts. That's why the table has no row at all for 1, 3, or 5 odd vertices. Impossible with 4 odd vertices and impossible with 3 are completely different kinds of impossible. So is counting odd vertices really the whole story? There's one more assumption hiding in the test, and nobody ever says it out loud. Every bridge has to sit inside a single connected piece. That is the hidden assumption. In the language of graph theory, there must be exactly one connected component. In plain terms, everything has to hang together. Here's a counterexample. One island where A and B are joined by 3 edges, and another where C and D are joined by 2. Count the odd vertices and you get A and B exactly 2. The condition is met perfectly well. And yet this figure cannot be drawn in one stroke. So what went wrong? Because there is no edge at all between the 2 pieces. You can't get across without lifting the pin. So the precise condition comes in 2 parts. The graph must be connected, and it must have either 0 odd vertices or exactly 2. Königsberg was connected. It failed on one count alone, for odd vertices. Which leaves one more question. What happens if we build just one more bridge? Look at the map again. Let's lay down one new bridge between the odd vertices A and C. That lifts the degree of A and of C at the same time, each by 1. What was 3 becomes 4. Now A and C can leave as often as they arrive, so they turn into stops you simply pass through. That leaves only B and D as odd vertices, exactly 2. Right at the limit the rule allows. Impossible flips to possible. An Eulerian path has just been born in this city. With one catch. It isn't a circuit that brings you back to where you started. The start and the finish have to be different. Let's verify it in code. With 7 bridges, impossible. With 8, a path exists. The actual route drops right out. Start at D, cross all 8 bridges, finish at B. Number the 8 bridges, and the single unbroken stroke appears right before your eyes. One bridge flipped the city's fate. All it did was take the odd vertices from 4 down to 2. From now on, any figure connected in one piece can be judged on the spot. The method is almost absurdly simple. Just count the red dots, the odd degree vertices. Let's judge 4 famous figures at once. The red dots are the odd vertices. First, the envelope, the little house shape. It has 2 odd vertices so it can be drawn. But you can't get back to where you started. You begin at one odd vertex and end at the other. Next, the square. All 4 vertices have degree 2, so wherever you start, you come right back. The bow tie, 2 triangles sharing a vertex, has no odd vertices either. Another circuit. Last, the complete graph on 4 vertices. Every degree is 3, so all 4 are odd. So it's impossible for exactly the same reason Königsberg was. What Euler really left behind wasn't the answer to a bridge puzzle. It was something far bigger. He gave the world its very first geometry that never measures length or angle. Stretch the bridges like rubber bands, squash the islands. As long as the connections match, so does the answer. Drag the 4 vertices anywhere on screen and the connections and degrees stay put. We call that an invariant. The field that studies only what survives stretching and bending is topology. Euler called it, in Latin geometria situs, the geometry of position. That became the seed of topology. And he didn't stop there. For a convex polyhedron like a die, vertices minus edges plus faces is always 2. For a cube, 8 minus 12 plus 6 is 2. Count up a tetrahedron, and it's 2 again. For any polyhedron you can stretch into a sphere, this value is always 2. We call it the Euler characteristic. Without this power to reduce the world to dots and lines, Google Maps could never find you a route. Great mathematics doesn't hide in grand places. It hides in an ordinary walk across a bridge. Next time you see a map, count the odd vertices before you touch the pen. The answer is already there. If you enjoyed today's video, please subscribe, hit like, and turn on notifications. See you in the next story.